So if relativistic mass is a useful lie, what is actually happening when things get closer to the speed of light? Well, we're going to equation town, so buckle in. You may recognize this equation, the equation for momentum, P equals m times v. Momentum, for anyone who needs to know, is how hard it is to change the speed of something, whether that's increase or decrease the speed. And this seems pretty intuitive. If something is very heavy, it's hard to move. If something is moving very fast, it's hard to slow it down or speed it up more. And that is where the original notion of relativistic mass came from. Since momentum is increasing because you can't get faster than the speed of light, then you would assume mass gets bigger. And that's actually a really great way to teach relativity. But the thing is, this equation is really only part of the picture. It's another useful lie. This is the real momentum equation. You've got the original momentum equation, and then you've got this extra term here. And this is the key. C, again, is the speed of light, so it's a very, very big number, which means that at low velocities, this whole term here, the square root of 1 minus v squared over c squared, is pretty close to 1. V squared over c squared is going to be some very small number, which means it's going to be 1 minus some very small number, meaning it's just going to be close to 1, meaning you could erase this whole thing and just do p equals mv, which is what we usually do. But you could see as velocity gets closer and closer to the speed of light, this number becomes smaller and smaller and smaller because this term gets closer to 1. At which point you're taking your normal momentum and increasing it even more because you're closer to the speed of light. Hence your momentum and thus your inertia increases without your mass increasing. But we use the useful lie of relativistic mass because a lot of the effects you see from your momentum increasing are a lot like your mass increasing. Though this does mean that you can't move fast enough to become a black hole just by moving fast enough to increase your relativistic mass, because again, that's not really happening. This also means that the Kugelblitz doesn't really work the way that power scalars think it do, but I'm not kicking that hornet's nest today. Fun side fact, this is also another mathematical proof for why we can't move faster than light. Because if v was greater than c, if your speed was faster than light here, then this term would be negative, making this whole term an imaginary number, making this whole result basically something we can't interpret. And even worse, if you were moving at the speed of light, you would be dividing by 0, and just don't break the universe, okay? Don't break the universe.